Hi guys, and welcome to part 2 of our 4-part series on classification. So we ended last time by talking about the different forms of feature extraction that are mostly considered under bag of words methods. So we did a one-hot encoding, the traditional bag of words, bag of engrams, and then a TF-IDF transformation. And that's where we ended. Since then, I've added 2 more slides to this section that show you how to calculate similarity, because I realized in looking at this lecture that I had talked a lot about calculating similarity between documents and vocabulary, but I hadn't actually shown you how to do it. So let's add that right now and then continue on our path of feature extraction methods. So in looking at TF-IDF, right, what we can do is import from scikit-learn cosine similarity. And remember that cosine similarity is a measure of distance where 1 is perfectly the same thing, the same vector in our vector space models, and 0 means absolutely no overlap between models, between rows. And so if you want the similarity between documents, right? So these are our 4 sentences about dog biting men, dog eating food, okay? If I want the similarity between documents, what I can do is take my bag of words representation, which I will back up briefly and show you what that is, maybe. I'll back up some more. Where is it? Here we go. Right, this is where we've used fit transform to put it into the vocabulary by document format. And you just calculate cosine similarity of the representation against itself. And that will give you the similarity for all of the documents in that structure. Okay, this is something I could do as part of my feature extraction. And so I can see that there's a 1 down the diagonal. That's because it's the original text compared to itself. And then values on the off diagonal. Okay. Now this at the moment is the bag of words representation for engrams. So this isn't just single words at a time. And I can do that same thing with TF-IDF. And that's partially why they are slightly different. But they'll also be different because TF-IDF has this weighting feature, right? And so what we see is that because of the weights, we get some 1s in the off diagonal. And now the bottom half of the matrix and the top half of the matrix will be exactly the same because that's how a correlation, this isn't correlation, but that's essentially what it is, matrix works. Okay, so this one's sentence 1 versus sentence 2, and this is sentence 1 versus sentence 2 as well. Okay, now that's between documents. How do I do this between words? Okay. And so what we can do for that is just use the transpose function to convert the matrix to where it's words by documents or documents by words. And so we do the same thing. .t for transpose. There's also .transpose function. Okay. And this will allow us to do it by word. And so there are 6 words. And we could also put this into pandas. So there are 6 words, and this is every word compared to every other word. Okay. Now, I didn't do that for the bag of words method because we did bag of engrams. And so we're actually calculating like words versus pairs of words, which is a little odd, but you could do. And so I just showed you here. Okay. It's actually quite easy. And so that would give you information about the relationship of the words or the documents to each other. Okay, you don't even need a machine learning pipeline. But the goal of this lecture, these 2 lectures, is to teach you how to do feature extraction to put into a machine learning pipeline. This is just bonus. So from there, I want to move on and talk about distributed representations. So in the last lecture, we had a kind of 4 section, I'm just kind of trying to get back to it, 4 popular approaches to feature extraction. And we only covered the basic vectorization approaches. Okay, let's now get into distributed representation approaches. And then we'll only have a couple slides in the last 2 because they're not nearly as popular. All right. So we're moving from these vector space models. Now, the distributed representations are also still vector space models, but they're more complex vector space models because they're still creating vectors of numbers from text. Okay. And we're moving now more into the neural net representation. Okay. And this is meant to help capture context, because one of the big things that we saw with our bag of words systems is that context is really hard. Okay. And understanding different contexts where the words are polysemous, where they have more than one meaning, and that would be disambiguated by context, is very hard. So what can we do differently than what we've been doing before? Okay. And so we might say, okay, let's think about words as a distribution rather than words as a single entity. So the meaning of a word can be understood from the distribution, the context in which it appears. That seems obvious, right? Context clues. So this is distributional similarity. So if the word appears in the same distribution, meaning the same context as another word, they probably have very similar meanings. So I can say that these two words are similar because they have the same context. Okay. And documents that use a lot of the same context distributions probably also have a very similar meaning. Okay. And so, you know, if we were doing this in real linguistics or in an English class, we talk about this as connotation, right? So the distributional hypothesis is that words with similar contexts have similar meanings. Okay. And documents with similar contexts have similar themes, underlying representations. Okay. And so using a vector representation, making this math, that means they have similar vectors. This is a sort of setup that we still have with vector space models with bag of words approach. But now instead of saying, well, they have similar frequency counts in documents, now we're saying they have similar literal context. So we're moving from this idea of saying they have the same words and we don't really care what order they're in, to they have the same basic phrases, the same context. And those are two different levels of representation. So bag of words approaches or basic vectorization approaches don't really care about word orders so much. They think about, if they have the same words, they're probably very similar and we can classify them together. And that's fine and good as long as you're removing stop words and all these words that appear sort of very frequently. But once you get into the problem of polysemy and ambiguity, which are two of the biggest issues in NLP applied computer-wise, you've got to come up with a different level of representation. So distributed representations move up and say, well, it's not just that they have the same words, it's that they have the same words in the same order, in the same chunks. So distributional representation are these like schemes that are obtained when we create a vector instead of the whole document of the context. Okay. So we're going to create a crap ton of vectors, all based on word windows or context windows. So instead of having a document vector, just one big vector of the count of the number of times the word occurs, we're going to create a whole bunch of mini vectors for each document based on the context that words appear in. Okay. So it's the same practical idea as a basic vector space model, but now moving in and saying, okay, well, I'm going to take these little chunks of the text at a time. Okay. And so let's represent it practically as a high dimensional vector rather than a simple vector, because each document has multiple vectors. Okay. And that creates a co-occurrence matrix of the word and its context. So we can still pull out the individual tokens, but now I don't need to have this n-gram representation. I'm basing it on my context level representation. And then these are reduced mathematically. Okay, so at the moment, that's maybe not necessarily different from a bag of words method, right? This is the time that it becomes different. Okay. And so in traditional vector space models like LSA, for example, or TF-IDF, we are so with TF-IDF, we are changing the numbers represented in the vector to be a weighted importance. In a distributional system, we're actually compressing the words, usually, into dimensionality. So what we end up with is a document by dimensions matrix. Okay? You can also get the words by dimensions matrix. How much does each word represent each dimension? And then how much does each document represent each dimension? So it's compressed, reduced mathematically from all of these contexts to these types of matrices. So LSA fits in this category. Topic models fit in this category, where you are taking the large amount of information that's available and compressing it. Okay? Why would you do that? Right? And the point of doing that is to capture these underlying latent pieces in the text. So more traditional math, statistical analyses, principal components, and exploratory factor analysis also do this. Like I have all these questions, but they're probably all representing the same kind of thing. So let's compress it down and reduce the dimensionality of the matrix. Okay. And that's really useful because then we get this weighted importance of how important is each word to each dimension, and how much does each document have each dimension. Okay. And this solves some of the sparsity problem. By this compression, we lose a lot of the zeros and we end up with weights instead of a ton of zeros. Now you can still have zeros, but you don't have nearly as many. And it helps us represent these themes or these topics, if you're doing topic modeling, based on context. Okay? So this kind of compression is really good for us. Okay. Now, another way that people, so you can use topic models and LSA. We use those in our text summarization section, but you can use those to create feature extraction. So you can extract a document's by topics matrix, which we did in a lecture a while ago, and use that information to predict which category they should go in. And then in LSA, you can do a dimensions by documents matrix as well. Okay, so those are valid feature extraction methods. I don't tend to see that they work very well for me. This method I'm about to explain works better about half the time. Okay. So while I'm suggesting that this is way better at pulling out context, I will also say that word embeddings have been hit and miss. They don't often provide me something better than TF-IDF. So that's just my experience though. Okay. So let's talk about word embeddings. Okay, people are obsessed with word embeddings right now without necessarily understanding all the connections between these objects, right? So word embeddings are practically bag of words in a different format. Okay, so it's helpful to kind of see how the growth of this field, the order that we have done this in really represents the sort of mindset shift that has happened across time to get to where we're at now. Okay. So embedding is the process of taking these words by document basic representational systems and converting them into a distributional representation system. Okay. Embeddings are, what that does is it helps create these high similarity vectors for things that are similar in context. And so just like factor analysis, it helps compress and say, these are the most related things, these are the next most related things, or like a cluster analysis, grouping things together. Okay. So let's say if we want to find something similar to the word beautiful, what do we mean if we're saying I want to add a thesaurus representation for this, right? So distributionally similar words have the same context, so you might be able to use a different word and it mean the same thing to you as a human, right? So these are things that are synonyms or antonyms, because antonyms actually have the same context. Okay? So we're probably saying things like pretty, attractive, ugly is an antonym, and so on. But that's just something I know because of my background knowledge on the semantics of this word. How would I do that in a word system? Well, I would create embeddings of where the word beautiful occurs in context, And then I would find context that matched that one and pick it out. And that is the basic concept behind Word2Vec. Okay. So Word2Vec, one of the most popular word embedding models. We've kind of moved on now into some of these deeper learning models like BERT and Elmo. But one thing I really like about Word2Vec is that it's fairly easy to implement using Gensim. And it's also 10 years old, which makes me feel weird. I feel like it just came out, but it really is good at representing context. Now, is context always useful in a machine learning prediction? No. Okay. Sometimes bag of words works great. So there is no one answer for which feature extraction method is best. And I'll reemphasize that in the next set of lectures. We actually talk about how to put these into pipelines. Okay. But first, let me tell you about Word2Vec, because it's a cool model. It's from Mikolov et al. This is mostly developed by Google. Okay. And it's a simple neural net. What the heck is a simple neural net? Well, neural network models have an input layer and an output layer. Okay. The input layer is the context, things that are going in, and the output layer is the prediction of what should be happening. Right? So if I'm trying to predict the next word in a sentence, the input layer would be the first words and the output layer would be the next word. There's a hidden layer between the two where the magic happens. And this is meant to mimic brain processes because there are a whole bunch of neurons that we don't really, they do things. The magic. Okay. Practically, this is a lot of math and a lot of tensors, little mini vectors. But the idea is that we input it into the system. The probability calculations happen, and then we get our outputs. Simple neural nets that's it. Input layer, one hidden layer, output layer. Deep learning models are neural network models that have multiple hidden layers. Okay, with different structures. So if you've heard of a long short-term memory model or a convolutional network, we're talking about the different types of layers that are available. Word2Vec uses one hidden layer in the middle. Okay? And so it is a simple model because it has one layer. Sometimes they're called shallow models. I think simple model is a little bit easier to remember. Okay? And so what they were able to do when they first presented Word2Vec was they said, okay, if you create a vector for king and you subtract the vector for man, then you add the vector for woman, you end up with the vector for queen. Okay? And this implies that that context is embedded in such a way that these things can be mathematically transformed. Okay? And then it was able to represent other kind of analogies like that one. This is their most famous example. That king minus man plus woman equals the vector for queen. Very close, okay, approximately. And so that's really cool that just using text that uses these words, we can see these relationships without reading. Okay? Now, there's a very similar model called fast text. That is the Word2Vec built by Facebook. So they took these ideas from Mikolov and changed some of the implementation on them. I find the results to be very similar, but that's because I'm not working with the types of data that they have. But the fast text is another option. Practically all the components we're going to talk about, they're exactly the same. Come on, close. Okay. And then there's one more that's really popular called Glove, and that one's built by Stanford. Fast text and Word2Vec are both implemented very nicely in Gensim. Okay. So the word representations themselves are low dimensional. They're dense, meaning that the vectors are non-zero. Okay. And the embedding is designed to capture the context to ensure that we get the best meaning of the word in context. And so this solves our problem of knowing if it's bat, meaning the animal that flies around, or if it's bat, meaning I hit the baseball. So it uses the word neighbors to help embed that context. Right? So we've been talking a lot about context, but what do we mean by that? It's literally the words around it. It's not that complicated. And you're like, how's that different than bag of engrams? Right? When we're not counting the frequency of that context, we're embedding those context Cs, and if they occur more often, they get more stronger weights. So we're kind of representing frequency in a slightly different way. So let's look at some pre-trained embeddings, because you can download pre-trained models before jumping into building our own. Okay. So pre-trained embeddings are available out in the wild, right? Meaning just different websites. There's some really great one there's a publication in behavior research methods called Subs to Vec. Okay, it's actually a fast text model, but it is a pre-trained embedding set of an entire language using subtitles. Okay. There are ones developed by Google. There are so similar to the BERT models that one can download, right? So you can check out Subs to Vec, but you can kind of think them like a dictionary. So given certain words, here are the contexts and the word vectors available. So if I said the word beautiful, here are all of its little mini vectors of contexts and their embeddings. Okay, so each document is represented by multiple vectors because it's got all of these different contexts. And each word is now also represented by multiple vectors because of all the vectors across documents. So we've taken this words by documents matrix that originally just had a number in it, and they're now representing each cell with multiple context windows. Okay. So it's kind of going from, that's why the little individual contexts are low dimensional, but the whole model is high dimensional because you have words by context by documents matrix, as opposed to just words by documents. So let's look at this pre-trained model. Okay, I'm gonna load this bad boy up. So I'm gonna load Gensim. Okay. And as long as this .bin file is in the same place as your Markdown or Jupyter that you're working with, you can load it up by using keyed vectors.load to word to vec. Okay. And so I can print out word to vec model .index to key. Index to key tells you how many vocabulary words there are, because they do get, each individual word gets a number, because it's saved in kind of a tuple list format to save space. So this particular model has 161,000 words or different tokens. And let's pull out beautiful. So here's the array that represents beautiful. Okay. And so this is the word by dimensions matrix. Okay, so this is beautiful's relationship to each dimension. Okay. And using that, comparing it to all these other words, I can find the most similar words to beautiful using most similar function. And it will tell me the cosine here of each word. So delightful is actually the largest, which is kind of interesting, right? And this is obviously biased by the size of the training data and what's in, what's in the training data. So do know if you get something that you're like, huh, interesting, remember what is going into the model first. Okay. Lovely makes a lot of sense here. Charming, gentle, wonderful, seductive, gorgeous, cheerful, quiet, right? And so these are the cosines. These are very strong values. They have the same context. Now, we're not necessarily saying that they have the exact same meaning, although we are saying that context and meaning are tied together. Okay? So there is a difference between words that have the exact same meaning, right, from a dictionary, and words that are used in similar contexts, because we are also talking about shades of meaning, right? So beautiful and pretty have slightly different meanings. You're going to pick one over the other for a reason, but they have very similar context. The words that you use around them are often the same. Okay? And we're using context as a window into meaning. It's not perfect. Okay. So let's talk about the differences in the model structure that you can have if you're going to train your own. Okay. And this will also explain exactly what a word-to-vec model does. This is one of the cool things that you can do with it, is I can pull out similarity, just like I showed you at the beginning of this lecture for these other models. But like, what is the purpose of one of these models? It's not just to calculate word similarity. That's just a handy feature in the background. Okay. And so when I'm building my own word-to-vec model, I have two big choices on the way that embedding happens. Okay. The embedding process. These are not all the parameters, but here's probably the biggest parameter difference is the way it gets embedded. And first option is called CBOW, or continuous bag of words. And if you look at the model we pulled in, it says CBOW. It's a CBOW model. And Skipgram. So let's talk about CBOW first. So in a continuous bag of words approach, the embeddings are created or trained to predict a word given the context on either side of the word. Okay? So the goal here is to predict the word in the middle, given the words you see on either side. So the actual point of a word-to-vec model is to predict a word in context, because then we have all of the information about context embedded in the model. And if I wanted to use that for feature extraction, I could pull it out and see if that helps me classify models. Okay. But word-to-vec is not a classification machine learning model. Okay. I mean, I guess it is, but its goal isn't to predict the category outcome. Its goal is to predict what word happened given a context. But given that embedding, those numerical vectors, it can be used for feature extraction. Okay, so we're leveraging this model to potentially use for feature extraction purposes. But its ultimate goal is to predict words in context. Okay. So what that does is it creates this probability distribution of the words. So if I have the context, here are all of the words that potentially could go here in the middle, right? So I've got my words on either side. And I'm predicting the one in the middle. And I have a probability distribution. The most likely word is this. The next most likely word is that. So it, it gives you all of the words that are probable for that slot. Okay. And then it assigns a higher probability to words that have been seen in those contexts before and are more likely. Okay. And then assigns lower probabilities to words that are less likely. Okay. So let's look here. Let's say we're trying to predict the word jumped. And so our word window here is brown fox. The word jumped is what we're trying to predict over the. Okay. So you don't take out stop words in this kind of scenario. Well, I suppose you could, but they're holding up the sentence, so you don't need them. You don't need to take them out in these approaches. So our window size here is 2. There's 2 words before and 2 words after. And we're using the whole context to predict the word jump. Okay, so we'll make a distribution of words that have very similar contexts to that one, and then rank them based on their probability. So the window size is the amount of words you get on either side. Okay. I've seen 5 as a really good option. Some people pick larger. Kind of depends on the size of the text. This is a parameter that you can tune and look for the best one. We'll talk about hypertuning in the next lecture, maybe the one after that, but in the next couple of lectures. 5 is a good one because it just grabs, it's a fairly large context. It's actually 10 words, 5 on each side. If you think about what humans can do, it's probably about 3 on each side, but try a couple different ones, see what works best. Okay. So it grabs the tokens on both sides of the window, the word on either side. Okay, so it's important to remember that's not the total window size. That is the, so it's 5 plus 1 plus 5, so it's 11 words total. And it embeds the word in the middle, given that context. So it creates a little vector for that context So it says this word is this context. This word is this context. And so that creates a ton of training examples, right? But more text is always better. So it gets some different options. It sees these words more than once. So it has more than one context window for each word. Now, how this happens is it's a sliding window across the text. So if we go back to our quick brown fox, we would have 1, 2, we'd predict brown, 3, 4. And then we'd move over one window. We say quick brown, predict fox, jumped over. Then move over one more. Brown fox, and then jumped over the, move over one more, jumped, fox jumped, predict over the lazy. Okay, so we're moving across the text. So one text object, instead of being 1, 2, 3, 4, 5, 6, 7, 8, 9 words, ends up being like 5 or 6 windows. Okay. Now these words will repeat. So using one instance, it doesn't look like a whole bunch more training examples, but you're not going to use the twice here. Instead, you would have a whole bunch of windows across a smaller vocabulary. And so here's a more written out example of how that works. So you would say the target here, because it doesn't have any words before it, is you get quick brown and the target word is the. You get the brown fox predicts quick, the quick fox jumps predicts brown, etc. Okay. So we end up with a bunch of examples. Now, given that this is a distributed representation, we take all of these examples and their probabilities and we compress it, right, into dimensions. This is what the hidden layer is doing. And so instead of having a document by windows matrix, what we have are these dimensions, okay, rather than documents. But the cool thing is we can get documents by dimensions out of there, or words by dimensions. So dimensions are meant to represent these underlying themes. We're kind of taking all these different contexts and putting them together into like this group of things and that group of things. But they don't have labels or anything like that. Okay. Oh, that is not a very large picture. Let me see if I can make it bigger. Oh, I printed out kind of small here. Ooh, CBOW 1. Nope. Just kidding. CBOW 2. How about CBOW 3? All right, that's a little bit bigger. So the way the model works is it gets an input. Okay, so the word in the middle here, word -1, word -2. This would be a 2 size window. Word +1 and word +2. All of those inputs are summed. Okay, their probabilities are summed. It's not probabilities, they're weights, right? And we get the pick the most likely output given those probability distributions. Okay? And so we get the word that we're predicting. Okay, this is the more conceptual model. The more mathematical models over here, right? We have an input layer of all of the word vectors by context. The hidden layer compresses them through dimensionality, and it feeds into the output layer, where an output layer is all of the vocabulary and creates a probability distribution. Okay, so these are the input words, right? And they're different their context windows. The input layer says, okay, here's all of everything I know. And given everything I know, right? Here's the likelihood of each of those vocabulary words. And a lot of them are probably 0. But then it picks the most likely one, which is where here we get this output. Now, how does it do that? So V is vocabulary here, D is for dimensions. Excuse me. W is window, and X is the new kind of the current context window that you're inputting. It's the input to the system. And Y here's our predicted word. All right, so the input layer includes the words and context from a new example. This information is fed into the hidden layer. It's kind of meant to mimic the hidden layers in the brain. So there's a lot of sections of the brain that does stuff. Okay. There's a lot we don't understand about the brain, but there are a lot of neurons. There's no like one neuron for the letter C, right? And so it's the way that this tends to work is it's a lot of neurons that fire off and you go, ah, cat. Okay? And so this hidden layer is created by taking a lot of these patterns that we see, because we're very good at pattern recognition as humans, almost too good at this, because it tends to deceive us sometimes, but it creates those patterns that we then interpret as probabilities. Okay? So from hidden layer, they're fed through softmax function, okay, this is math, to create that probability distribution over the vocabulary. So given everything we know, what is the likelihood of this word being in this context? And the output is our final choice with the highest word probability in the vocabulary. So how does it learn this? Right? This is a model that learns things, or it gets trained by looking at all these examples. Well, what happens is you'll feed it a new example and it'll predict a word. Okay, even though it's only ever seen maybe one word before. And when it predicts that word through back propagation, which is a type of system that feeds back the answer. So it says, here's what I think the answer is. And then the model goes, whoa, you're wrong. It should have been dog, not fox. Okay, just making up something here. And the model goes, oh, okay. And so it tunes the weights in the hidden layer to get closer to the answer. And through lots of many trials and training epochs, it'll tune the weights till it's getting the answers right. Okay. And so sometimes folks describe this as loss. Okay, loss is the amount of change in the parameters. And you see this a lot with deep learning models where you can tell it to print the loss as you go, so that you know how well the model's learning. And you basically don't train it so that well, hold on, let me say this better. You train models until the loss evens out. Okay, it asymptotes close to zero, so that you don't overtrain a model where the only thing it'll ever learn is the examples it's seen, but you give it enough examples so that it's not changing a whole bunch every time you use it or train it. Okay? So you want models that have learned what they can learn, but haven't forgotten that they can learn other things, I guess, would be the way I put it. So a lot of people will use that loss function to know kind of when to stop. Okay? And this is through back propagation. So it's just subtracting how much are the weights changing. If the weights aren't really changing, you've learned what you're going to learn. If the weights are still changing a lot, you might be able to learn more. Okay? Now, that's the first big model. Okay? Conceptually, this makes a lot of sense, because what we're doing, if I still have the picture open, I don't, let me open it, is we're saying, okay, well, here's the context. The summed weight of all of those contexts is what predicts the output. Like, that's what controls this math here. So it's all of the words together predict the output. In contrast, what we could think about is that there might be one word in there that's really key, and the other ones are just support and cast. And that's the idea behind a Skipgram model. Okay, it's a very similar embedding algorithm, but instead of having a summed representation of context, the entire context, where all four words in this two-window scenario are used to predict, each context pair is embedded. So brown and jumped get embedded together. Fox and jumped and over, jumped and the, separately. So the embeddings, instead of being, here's the window, all of them are summed up together. It's here's these two words and these two words and these two words, and they all appear together in context. Okay? So the pairs are embedded rather than the entire context window. All the other parameters are basically the same. Like you can tune them in the same ways. Okay? So let's look here. In comparison, right? So the quick brown, you get the target word, the, and then the context quick, the, and brown. So notice here you're gonna have a lot more examples, but the context windows are smaller. Okay. Now let me make this one a little bit bigger too. Skipgram. This one. Okay. Just so it's a little bit more readable. So in this scenario, right, we get the original word as our input, and we are predicting the context that it went in. So it's kind of backwards, but each pair is tied together. So we input, here's the word beautiful. What context is that word going to appear in? Here's the words that it appears with. Okay? And so it works in the opposite order. We have our input layer of the original word, right? Our hidden layer, and then a softmax function for each of these, and our output layer where we're predicting the probability of each vocabulary word given the original input word at t-2, t-1, t+1, t+2. They just didn't have enough room here. And so this is a continuous skipgram model. So kind of getting the whole context, predicting one individual word versus getting the word and predicting the smaller context pieces. Lies here. All right. So, but otherwise the models have practically, it's like one mini little spot to change in Gensim. So you actually have to be careful because it's very easy to ignore that parameter. But some other parameters, what are some other important components to Word2Vec models as a whole and not just Skipgram, right? So it says Skipgram up here at the top of the slide, but this is like Word2Vec as a whole. Okay? So the number of epochs, this is the number of training epochs. How many times do you want to train it? Okay? As people, as humans who have learned to read, right, and speak, you have heard or read many examples of the exact same context in your life. So over and over and over again, you know, thank you, happy birthday. So we would train our models to see the same examples. That's not a bad thing because that is how language works, right? The learning rate, so the rate at which the model will learn. Negative sampling, which sort of deals with forgetting and loss and, you know, making it a little bit messy so the model isn't perfect. Okay. And there is a really great Towards Data Science article that tells you about like how all of these work and what some good starting points are and how to tune them. So I'm going to import this common text. It's actually not a very good data set for this, but to show you how this can work with very small datas, okay, we're going to import common text. So if you look at it, it's literally just like a list of key phrases that are common, okay, in data science. And we're going to build our model. Now, assuming that you've imported the Word2Vec function already, okay, you put in the tokenized list. So Gensim, unlike the count vectorizer and the TF-IDF transformer, where you just like stick in all of the text and you're done, Gensim does require you have a tokenized list. So it's a list of documents that have been tokenized. So you do have to tokenize it first. Okay. You put in the vector size, that's the number of dimensions. Okay. If I had a large text corpus, I would probably start at 300, just because there's some research that shows that that's a good number. This is a small text corpus, so I went with a smaller number of dimensions. How to pick the best dimensionality is difficult because this is sort of, again, meant to represent like what's going on in the text. Okay. And so if I was using this as a feature extraction method, I would get 10 predictors out of this model. Okay, so that actually is the number of predictors. But you don't want to have too many dimensions or they're going to start to basically be the same column. So you got to kind of think about the size of the text, like how many different kind of themes do you expect there to be in the text? And so there are a lot of things that might be represented, but when you have a very small data set like this, go smaller. The window size here is 5, so that's 5 on the front and 5 on the back. SG equals 0 makes it a CBOW model. SG equals 1 makes it a Skipgram model. The minimum count is the minimum number of times a word has to appear in the corpus to be included. So 1 is the lowest. And workers, if you have a nicer computer, it will parallel process and make this a little bit faster. So workers equals 4 is 4 parallel embedding procedures. Now, this data set is small, so it's very quick. Okay. What are the most similar words to computer in this example? Okay, so WV, our model.wv.most similar. Okay, computer, give me 5 of them. So we got EPS, trees, miners, survey, and interface. You can get negative values here. Print our model computer. So I can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm getting the word by dimensions matrix. And these are extracted from the words by dimensions matrix. So if I want to do more than that. Okay. Now, what I will do in the lecture where we're actually building our machine learning pipelines, I'll show you how to extract the entire dimensions matrix so that you by documents, dimensions by documents, and actually I might have it in this lecture too, but I'll show you in a minute how can you get out the document information so that I can predict which category a document should go into. Okay. Actually, I'm going to show you right now. I couldn't remember if I put this here or later. So here we are, it's here. But what if we want to predict word, like my goal isn't to predict what word and context this is, because the whole point of this chapter is classification of documents. I want to know if this tweet is hate speech or not. Right? So when you have a high dimensional space like this, many representations for an individual word, they're represented in these mini small embedded vectors. So I have this like words by dimensions matrix, but how do I get back to the documents? Because that's what I need. I need a score for each document. So how do I create a documents by dimensions matrix? Okay. So effectively, we just kind of say, okay, well, each document is a sum of its parts. So we're going to sum up the word vectors for each document. Okay. And so we end up with a document by dimensions matrix. And this I took from a different book, but I think it's really great. So we're going to use NumPy here. And to kind of walk you through what a lot of this does, it's a flattening function. So it takes it from high dimensional space back to low dimensional space, but it's the crunched version. So it's not like it's a documents by words matrix, right? This is a documents by dimensions matrix. And so we put in our corpus the trained word-to-vec model and the number of features that we want back. This is the number of dimensions that you get back. Okay. It's going to grab the vocabulary. Okay. It's going to average word vectors for each word in our model and its vocabulary, given the number of dimensions, sum up those features. And so for each word in the document across the vocabulary, add them up. Okay. If you've reached the last one, divide by the total number of words. So add them up and divide, right, and return that bad boy. So we put in our corpus, which is our common text, our model, and our number of features. The common text number, the first common text is human interface computer. Okay. And that returns an array of the average context for each dimension. Okay, given, this is probably only one context actually, because, but for each word, it's got its own little context window. So humans got interface and computer, interface has human and computer has human interface. So there's 3 contexts there, and it's creating an average context for each dimension. So it averages all 3 context windows for each one and spits out now a document by dimensions matrix. And that is what you would predict with. Okay. Now, you can also get these directly from Spatie, okay, given that Spatie is a neural net. It's already got this stuff embedded. So if you don't want to build your own embedding model, you could use an English model to predict from. Okay. Now, the good thing about this is that it would work on a large number of different types of vocabularies. The bad thing about this is if you're ever using a specialized like you're trying to predict specialized documents. So in the next lecture, we will do an example of the Java development kit bug corpus. That's going to have a lot of specialized words in it that are just not going to be represented well in a Spatie English model. Okay. So if you're trying to predict information that is common speech, like news articles, right, or literature books, those might be represented pretty well by Spatie. So don't train your own model, pull it out directly from Spatie. But if you're using a corpus that is sort of specific to financial markets, for example, you might consider building your own first. But we can run our NLP on it, right? And then we can get a vector for each word. Okay, so for our document, grab its vector, right? Sorry, so this is the, this little quote here is for the next printout. So the vector for Canada is here, right, given their dimensionality. If I want the average vector for the entire sentence, right, this would be the document by dimensions window, for example, in this in Spatie, this would be the vector. So we could just run through each document and grab its vector and then use that to predict. And that might be a little bit faster than training your own model, depending on how many examples you have. But again, if your model has specific vocabularies, I would train your own because it doesn't take forever. It just takes a little bit to run. So you could set it down and go to lunch and probably get back and have a trained model. Now, other things that we can do is we can actually move up to document level representation, and we'll get to that in just a second. But what are the pros? Context. That's the whole point. We've moved up here. Now we're capturing that context component. There's lots of potential word meanings, and this might help us disambiguate different word contexts. It is still hard to handle the out of vocabulary problem. Okay. And if the corpus is really large, it can take a long time to train, but you only have to train it once. Now, in this sort of representation, we can actually deal with the out of vocabulary problem. So it's still something that is not naturally handled by the model, but we could build a model that is designed to deal with it. And so what people do is they make contexts out of lexical components, right? So category could be represented by its phonological level. So ka, at, e, go, re. Okay, so we could separate that. And if we get into a new word that we've never seen before, like, I don't know, I can't come up with one. Catalog, let's just say, we've never seen the word catalog before. I can grab the cat from here, the E here as well, and then a log from somewhere else and combine those together. Okay. So we could use the word with the strongest match at the phonological level, or we could play mix and match and grab all the right phonemes and throw them together. Okay. Fast text actually does this by using an n-grams approach to match. So for example, if we have a gregarious, it would break the word into trigrams, which are 3 little letters at a time. And then those n-gram embeddings are combined to create the word. So if you've never seen the word gregarious, it will go find a GRE out there, the embeddings for GRE, find the embeddings for REG, and then combine them together to create the new word. Okay? And that's not a terrible idea, because in most languages, including English, words are roots of each other. So like strongest, okay, strong and est, right, are two separate morphemes, meaning units of meaning. And so if I took the units for strong and the units for est and combine them together, I'd actually get a really good representation of that word. Okay. And so it's not a terrible idea, but this is how you might handle the out of vocabulary problem. Okay. And this is a natural thing that's built into the model. Now, if I want to move up and beyond the word level, okay, there is another structure called doc-to-vec that takes this word-to-vec architecture and instead applies it to the entire document. Okay, so it will learn itself. It will learn what's called a paragraph vector, and it ties that document parameter to it. So it has a similar structure to CBOW and Skipgram, but the names are totally backwards than what you might think. So the distributed bag of words, which kind of looks like CBOW, is actually a Skipgram model. So here's the CBOW version on this side, called a distributed memory model. And what it does is it remembers the paragraph matrix, like identifier, and all the, oops, sorry, I got excited, and all the context. So it sums the paragraph identifier with the context. So all of the words get summed together through the hidden layer to predict the individual word. Okay, that's a CBOW model with an added paragraph predictor. In a Skipgram model, or the distributed bag of words, we have this paragraph ID is used to predict what the context would be. Okay, so that paragraph is tied to each word individually, and that's a Skipgram. Okay. And so you can tell by the way which order they're predicting in. So doc-to-vec is also built into Gensim, and it just helps embed the document it's called a paragraph ID, but the document level ID. I've not played with doc-to-vec too much. I've just built a couple of them. I think word-to-vec is a little bit easier to work with, but that's my personal opinion, because doc-to-vec could be useful for classification components, because it embeds the ID of the document. So that's our neat little bow for distributed representations, but universal text representations sort of fit under distributed. So this is part 3 of the 4 parts, right? And so everything that I have talked about for like 2+ hours across both of these videos focuses on the word. I mean, like, no matter what, we've got individual word tokens here, and we're putting them together into vectors that make little mini context windows, but it's on the word level. And that makes some sense, because words are what create meaning. However, polysemy is a big problem, okay? And so remember that polysemy is the fact that words have different meanings depending on their context and their use. So we've got bat the animal versus bat the baseball bat. So how do we make sure that we have a better understanding of contextual word representation? How do we get that connotation out? And this is one of the biggest components to hate speech, right? Because in some contexts, some words are okay. In other contexts, they are not okay. And so if you're only banning certain words, that's like a sledgehammer to the problem, right? You get rid of all of those words, but it's not, it's not always a bad thing. And so how do we contextualize our prediction a bit better? Okay. And the solution is much like Google does when you use their search algorithms. Okay, so we might predict the next word from the previous words, okay, which in word-to-vec would be half of the window. Okay. We could use things like Markov models. Okay. So a lot of folks think that the search algorithm for Google is a Monte Carlo Markov model. Okay, we could use the hidden Markov models that we covered, continuous Markov models several lectures ago, where the combination of the probabilities of the words before it are used to predict the next word. Okay. Or what's popular now are called transformers. Okay? And these are meant to represent words just a bit better, okay? Because it's better at grabbing context. So Word2Vec was the original plan for context. And a lot of people were like, wow, that's cool. How can we do better? And so a lot of folks now use like recurrent neural networks and transformer systems. So like BERT's an example of a transformer system. They're very complicated. I didn't want to get too much into them, but if you want to Google transformers, language modeling, because otherwise you're going to get the movies, you can learn a little bit more about them. Okay. And so these models are large. They're very big. You can download them, use them. Okay. And then we'll cover the reason we're not going to cover recurrent neural networks right here is because when we build those deep learning models, we're not feature extracting anymore, right? You're building them. Here's the input text. Here's the answer. Learn it from the middle, right? And so they're their own machine learning thing. They're separate. They've got the feature extraction and the model pipeline all built together, okay, in one system. Right now we're covering how do you do the feature extraction and then put it together with an algorithm. And then we'll talk about the deep learning systems, which are a combination of those two. But you have to think about what your feature extraction might be, right? Because in an RNN, for example, you might want to embed a certain amount of context. So thinking about these feature extractions can help you build the right type of deep learning model if you want to go there. Okay. So Elmo and BERT are these like giant transformer models that you can download to use. I have heard from some folks that they can be a bit difficult to set up, but otherwise can work really well. And they're trained on just bazillions of different examples. So they tend to generalize to lots of different contexts, hence the universal text representation name, as opposed to specific text level representations, right? So Word2Vec is at the specific text level. This is more like global stuff. And so the suggestion is to take these pre-trained models and add your own examples to it with a task-specific information. And so these can be hard to set up and they could take a lot of computing power. So my suggestion, as always, start with the simplest thing. Start with a bag of words. See if it works. If it works, great, stop. Because you've saved a ton of time and money. And then get more complex and see if the task requires that level of complexity. Maybe before you spend all of your time, because they're cool. I mean, don't get me wrong, I'm with you. They're cool. But if we don't need things that are that complex, you can save yourself a lot of energy and computing power. And computing power costs money. So our summary so far. Okay. Before we get into hand-coded text. So all representational systems, from basic level vector models all the way up to, if you go deep learning model, and transformers, are biased in the same way that whatever data is used to train them or extract them are biased. Okay. So, it's not that logistic regression is biased. When we get into machine learning algorithms, people talk about bias, algorithm bias. They're actually talking about the data that's input into that algorithm that's biased. So whatever data you have and the biases that are natural in that data are still there when their features are extracted. So it doesn't matter if you use transformers, bag of words, TF-IDF, Word2Vec, the biases are still there. Okay. So we have to think kind of long and hard about what the data can and cannot say. Okay. So if you only train something on news articles, it's going to think that apples are computers, not fruit. Okay. So a simple example of bias. Pre-trained systems that are any good are very big. Okay, so BERT is very big. Okay, built by Google, I think. And so we still really want to bring it back down to the application-specific problem. Okay, so what are you trying to predict? And what is the best data that could build a model to predict that? Right? If you're trying to predict all of English, a SPACY or a BERT model might be better. if you're trying to predict Stack Overflow questions for C++, that English model is not going to do you any good. And so thinking about the domain and content specific problem will tell you what type of data you need to find to help yourself build something for that solution. Right. And then we also have to always think about balancing the time and money, the effort versus the need and necessity. Okay. So it doesn't hurt to start with the simple systems because they don't take a long time to run. And if they work great, they work great and you move on. They don't work great, maybe you get more complex. So this lecture started from the simplest and definitely worked up to the most complex with transformers. So that is kind of the order I tell you to work in. Or what's normal also for your field. But even then, a bag of words might solve it. Now, a quick kind of fun side foray before we finish with the last of the four. So we have basics, distributed, universal text representations, and then we've got hand-coded, which is like time and effort, okay? But how can we visualize this stuff? Maybe that'll tell me something really useful about what's in the text. And I'm like super pro thinking about what's in the data, because I think there's too many applications or people or systems or whatever. There's this natural thing to shove it into the algorithm and see if it works and not understand like what's in the data and what is predictive. So let's unblack box some of this stuff, right? So visualizing these vectors, not only is it cool, right, might help us think about the method, the extraction method. What is this thing doing? And is it gonna be useful? And or is there something that I'm missing that might be a good predictor? So to do that, we can use I don't know how people say this algorithm. In my head, it's T-sign, but I'm pretty sure that's not right. Just like pronouncing R dplyr for the first time, right? So T distributed stochastic neighboring embedding. Okay, so it's actually a different embedding system, but it is really great at making cool pictures. Okay, so it takes high dimensional data and reduces it into low dimensional data. So 2 or 3 dimensions, I'd really stick with 2 to help you see kind of what's happening. So it kind of works like multidimensional scaling or principal components analysis. So if you've ever made a cluster, a k-means cluster, and you've put it on a little chart, that's essentially what we're doing, but with the word embeddings. So here's an example of the digits data set. So this is actually a picture one and not a text one. But if you represent pictures as feature embeddings, right? So you represent them as the pixel embeddings, and then tell this algorithm to cluster them, works pretty well. Okay? So what you see are these nice differences between those pictures and their representations. The other way that we could think about visualizing them is, again, putting the words on the screen. Okay. And so especially on this side, we can see that a lot of these words cluster together because they have very similar embeddings. It's kind of like cluster analysis, but it's not really meant to like create these clusters. It's just meant to visualize them. And so let's see how we do it. Now, this can be slow. I will warn you, it can be kind of slow, but you import it from scikit-learn. We're going to import matplotlib pyplot because it's a picture. I'm going to import Seaborn because I'm going to make a scatter plot effectively, pandas, and an LTK. Now, I pulled this from an example that I have because the example from the book, it's just like, oh, you can make these charts, and then it doesn't tell you how. So I added the how here. And I have a 20 news groups example from previous lectures. So I pulled out the 20 news groups and I classified them as their main group name and then only used a couple of the examples. Okay, so this is a example of data sets that people were writing about religion, politics, computers, sports, and something else. So I tokenized the data. I put it into my Word2Vec model because I've already cleaned it. I've done my pre-processing. And this is also wanting me to show you that you have to tokenize the data to go into Gensim. And so here's our tokenized data. I'm gonna say there's 20 dimensions because there's 20 news groups, why not? Okay. With a window size of 5, a CBOW model, and a minimum frequency of 1. I then extracted the features. So now I have a documents by features matrix. So this is the number of documents by 20 dimensions. And I'm going to use my TS&E algorithm here. So I'm going to say, okay, give me 2 components, meaning 2-dimensional. Okay. Verbose just means it's going to print this stuff out. Perplexity is a measure of like complexity. The higher you go here, the longer it'll take to run, but you cannot go over the number of dimensions, okay, or the number of columns. So I did half. Number of iterations here. Fit transform. This looks very similar since it's all inside scikit-learn, right? Fit transform this data set. And so it ran. Took 106 seconds. Okay, a couple minutes. Now I put it back in my data frame. So I said, okay, give me the first dimension, then give me the second dimension. So it's all in the same data frame. Calculate the first dimension as X, the second dimension is Y. There's no reason why one or the other, doesn't really matter. Color it by what category they're in. So religion, politics, science. Okay. Pick a cute color palette. So I'm like slowly learning how to make better plots here in Python. I'm much more of a ggplot person, but I'm doing my best. And here's the data set name. Now that's too hard to read. So let's put it up larger on this screen. Now these aren't perfect separations because people are still yapping here. So we've still got a lot of overlap. But what we can kind of see is some of the colors tend to cluster together. So I've got our computer, I'm pointing. I've got our computers up here in a nice solid green, which is overlapping science. Makes some sense, right? Our religion component is way over here, overlapping politics, which shouldn't happen, but it does, right? Let's see, recreation. So this is hobbies and stuff, right? It's kind of down here. I thought I had sports in here, maybe not. So we don't get it's not like the digits data set where they're perfectly separated because language does not work like that, right? A lot of words are used in a lot of different contexts, but still I can kind of see those separations with those embeddings. And so I can kind of get a feel for the dimensions might help predict here. I might be able to capture those. Okay. It's also just really cool. So last but not least of our 4. So tying all of this back down to the 4th category, which is handcrafted feature representations. Oh boy. Okay, so domain-specific knowledge is really useful, right? Because that's what we do when we read or we listen or whatever, right? We're pulling in our own background knowledge of how the world works. And so there are systems like Text Evaluator, written by ETS, the Educational Testing Service. Yes, that is the people who wrote the GRE and stuff. There's another one written by Danielle McNamara's lab called Cohe Matrix. Okay, and there's a couple more. And so these are systems that are written to measure certain objects, like complexity is one of them, coherence, like how easy it is to read, how complex it is, like what reading level this is at. So these are handcrafted features. And there are systems that will help you, that you could search for this, right? You could use your own lexicon and build your own scoring guide. So this is actually pretty popular in sentiment analysis. And essay scorers do this type of work, for example. Okay. Now, obviously, this is going to be the most time-consuming system. But if someone has already programmed a way to add this, you could take your feature extraction that you already have, add this information about documents, and see if it's a useful predictor. So these don't have to be in separation. I could do a TF-IDF and then add these other measures to it. Okay. So there's another one called the LINQ, Linguistic Inquiry and Word Count. It's based on proportions of words that fall into specific categories. That might be really good for a sentiment level analysis. So there are teams that have put together these specific extraction methods that are based more on conceptual ideas than just the individual words themselves. But custom feature engineering is time intensive to say the least. All right, so let's wrap all this up. You have learned a lot about feature extraction. A lot. 2 whole lectures worth. Okay, so there are a lot of feature extraction methods that all build on each other. Start with the simplest, work your way up to the hardest. Okay. We could also incorporate LSA and topics into this lecture, but I just didn't because it's already long enough. And so we could pull these features by dimensions matrices for predictions, just like Word2Vec. Okay. And you can always add other features: word length, part of speech, dependencies, key phrases. So the things that go into the algorithms, as long as they can be numbers, can be added to the features that we already have. Okay. And so next up, the next 2 lectures, we'll cover how do we take these numbers and put them into a supervised classification algorithm. Again, like, how do I build a model that actually predicts an outcome? Because all we've talked about so far is how do I take text and turn it into numbers. Right? So come back for the algorithms themselves, and let's see how predictive we can make a model to predict a couple of different data sets.